Okay, the record is on. So let us come back here. Okay, now the lateral load system itself, it's going to take some, explanation. So I'll try to not to get too much into it, but you can say that if we have a system, we need to have the lateral load system to withstand the lateral load. Okay, that can be achieved by using the framing system, the brace system wherever we can, because the framing system is just like the triangle shape. And if you guys should know that whenever we can have the triangle shape in the structure, this is the strongest shape. The displacement of the building will be down significantly if you can have the brace system like this. If you cannot have the brace system, you need to make sure that your frame here like this is strong and it can take the moment, meaning that this better be the rigid joint just like in the frame. So this is the main reason why we have to study about the frame in the structural analysis class. Okay. And this is the very important concept, because let's say generally if you have to deal with the frame of the warehouse or the factory, generally this is what you can commonly have. So let's say, because the factory, you need a lot of space between them, right? And it's going to be a very, very wide system, and it goes into that direction. You have so many frames in the longitudinal direction. Okay, generally when you have this as a hinge like that, and you have the load coming in like this, now you as an engineer will be the ones to give the details so that you have the behavior of the structure the way you want it. So if you give the details such that this is a hinge, and then you connect this piece of member into the column as a hinge, like that. So you have a hinge, 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 and hinge. What kind of system is this? Do you know? This is unstable. So your whole frame just can come down because it is unstable. You get too many hinges. So it is very imperative, very important that you know how to give the details properly. Now, generally, engineers don't wish to transfer the moment into the foundation, so they always give these details to make sure that the columns behave as a hinge. So when this a hinge detail is used, this has to be fixed, right? If the support is hinge, this must be fixed. Okay, so that means, can I say that if my support is fixed, can the top portion be hinged? Yes, suppose so. But the common mistake that people make is that this is going to look like a cantilever beam, right? You see that? This looks like a cantilever beam, because once you give the details so that this portion is a hinge, if this is hinge, this is pretty much like a standalone column. And you must know how to design a column like that looks like a cantilever beam like this. Okay, and most of the time you can You can also give this detail as a fixed, and this is also a fixed. This would be best, yes, but the next question would be, if you design it like this, you must know what kind of detail would work as a fixed form, right? So now, what you have always learned in the analysis class, mechanics of materials, when you draw a support, a roller, a hinge, and a fix. Now it comes a time when you must start to learn how you can achieve that kind of behavior. So this is the fun part of being an engineer, really, okay? Because you control the behavior. So when you perform the analysis, okay, this is what I want. I want this kind of behavior out of the structure. So after the analysis, you've got all the forces in the member and so and so. You must know how to make your analysis and all the details, all the assumptions you make in the analysis become reality. So that's why we are taking the design classes, to make sure how we can achieve the behavior that we want. All right. So we can come back here. Okay, so that's the whole idea of this picture, you know. All right. So see the next picture. If it's fixed up top, now our system becomes stable. Okay, and this is the example of the framing system when we cannot have the brace, okay, like that. See, no brace, and you have the full use of the area anywhere. See, we have the full use of the area everywhere, but look at the details of the joint. That looks very, very stiff, right? Because yes, that's a fixed support. Okay, so when the fix becomes you know, the behavior, it becomes like the typical rigid frame. And this is the moment diagram, if you can recall. Okay, and if you can have it, maybe you can negotiate with the architects that in some buildings that you can sacrifice one bay. You don't have to have every bay. See, you can see that this bay, there's a brace frame here and here and here. So perhaps they're gonna, you know, put the wall in that bay, so nobody's gonna see this frame anyway. And to have only this bay as a brace frame, it does help the entire system a lot. Okay. You will deal with the design of this framing system and so with Ajahn Sutat later. Okay, we have all kinds of braces available that you can select depending on the typical usage and so and so. So this is what it looks like. Okay, you see, notice one thing. Oops, that we have. This is what we call the gusset plate. See that? It's pretty big. The reason that we have something like this is that we try to make sure that, you know, the center line of the member will meet at one point. Like this. So when the center line meet, you know, you have no moment. It becomes like the truss system completely. If you cannot make that, it means that the moment is going to occur and the system is not completely a truss system. Okay. So here, more of the same, more of the same, more of the same, more of the same. And yeah, this is the system that I already mentioned. Okay, we have the brace frame for the factory or the warehouse, and you can see very clearly that in this direction, try to show you, when the wind comes in this direction, it's the frame itself that has to take the load, right? So the frame in this direction must be pretty strong because there's no help, and each frame will be all alone by itself. But let's say Let me erase this. When the wind comes in this direction, okay, it's gonna go, okay. Now what you will have to withstand the wind in this direction is the entire frame in this, right? So I can draw this in this direction. Let's change it to the blue so that you can feel it. In that direction, you will have a lot of frames work together in that direction. And generally, because of this side, you can put the brace here, okay, because you have the wall. So then in this direction, you don't have to have a very strong frame to resist it, because you have so many frames, and you can always put on the brace. But in this direction, you know, the previous one, where the wind comes in this direction, and I can draw that, you will, you will have only the frame itself to withstand the wind. So the frame will have to be strong in this direction. And can you see that? So that's a system. Okay. And okay, let's skip that one. Another thing that will be closely associated with us is a steel structure that we call the truss system. You should be familiar with this truss, right? Everybody should, because at least I believe you have done this in either the structural analysis class or mechanics of materials class before. The truss system is essentially the beam, but you use the truss to convert the bending moment into the axial force. But the truss is a very, very effective system. Okay, and truss, we have tension and compression. So if you know how to design tension members and compression members, hopefully you should be able to handle the truss. Okay. So we have so many kinds of truss system, and you can read details in here that it is a very, say, effective system and efficient as well, because it's light by itself. You don't use a lot of materials because it's so many open spaces in the truss, right? And we always use that as a long span system. You can also have so many other systems like this. This is what we call the castellated beam. It comes from the word castle. That yep, something like that. Castellated beam, where you cut the Y flange like this. So you have the Y flange. Your flange is here. You cut them like this, like a castle, like the fortification of the castle. And then you lift them and weld them back together to form a shape like this. So you will increase the depth of the section, and as a result, the moment of inertia. So it's very efficient, and it kind of looks beautiful in a way, but you have to deal with a few things more. First is it's going to cost more because you have to pay for the cut and the welding process, and then you're going to have to deal with additional failure modes, you know, that come along with this kind of configuration. Okay. So this is the truss system. Okay. Now, generally, there's no better time. I hope you can remember the truss. Can you? Okay. Please, I thought you guys are going to be more lively than the folks at KMUTT, but the more that we go on, you become a little more quiet. That's okay. Anyway, we have so many truss configurations that you can use. Do you know that the truss is a beam? Are you aware of this?
Yes.
Oh yeah. Okay, great. So basically, when you have the truss, it turns the bending moment into the axial force. So let's say if we have the typical truss system, like, do I have a better picture? This is a picture of the truss. Okay. I don't have it. Anyway, let's look at this. Let's go over it quickly. Maybe I will underline this more on our, say, special session for the design. If it's a beam, and if it's a simple beam, it means that you have compression on top and tension at the bottom. Am I correct?
Yes.
So if we talk, thank you. If we talk about a simple beam, you have the positive bending moment, it's compression on top and tension at the bottom. Meaning, if you design a truss as a simple beam, your top chord is going to be under compression. And your bottom chord, it's going to be under tension. Are you guys aware of this?
Yes.
Good. Okay. It takes a while. So I would just, it's already going to say something. And the top and bottom chords are the one that handle the bending moment, right? Because if I cut the section of the truss, let's say if this is a circular section, you're going to look at something like this. And the moment of inertia of the section significantly will come from the top and the bottom chord. And when you look at your flexural stress looks like this, right? Your maximum stress is top and bottom. So naturally, top chord and bottom chord will handle the bending moment. And you can certainly feel that if we have more depth, we have more moment of inertia, so the forces in the top and bottom chord will become smaller, right? And okay, that also means the maximum forces in the top and bottom chord will be in the middle, right? Because bending moment. So the maximum force will be in midspan. And for the shear, it's handled by the diagonal web members, right? Because the shear stress is like this. So the maximum is here at the neutral axis. So it has to be handled by this diagonal members. That's a truss system, because it's essentially, you guys agree with me that it's a beam system. So it works like a beam, yes. So all the webs will handle the shear. So that means the maximum forces on your diagonal or vertical web member will be near the support and with zero at midspan. You guys with me? Okay. Are you hungry?
No, but yes, I think so.
You're not with me, but you think so? That breaks my heart. Maybe, okay, maybe we will get to this later, but that's a system. Okay.
I mean, I'm not hungry, but I'm with you.
Okay, thank you. Thanks. You know, okay, thank you very much.
I'm trying to.
Okay. You know, the benefit of all the online classes is that you can always have your breakfast and lunch and everything, you know, without anybody knowing, right? Anyway, so let's skip this. We already mentioned this. Design philosophy, the law side. This is the example of the law stating that, you know, what kind of load that you need to design for. We already mentioned that. This is from another country. Okay. The concept, we already mentioned this a little bit. I'm not going to go much into detail because we already mentioned enough that in the end, you need to make sure that the resistance is greater than the load. Okay, but this is just to show how, you know, some brilliant folks have come up with the factor of safety or reduction factor. They consider the say probability concept. And if you study this graph more closely, you see that this is where the failure is going to occur. Here, in this area. This is where the resistance is lower than the load. See? So we try to avoid that. And generally, this is the normal distribution by Bernoulli. You plot all your stuff going on. So I'm not going to go much into detail of that. Some folks already collected the data for statistics, the live load and so, and also collected the data on the manufacturing process, how many errors can occur, because yes, when we say we manufacture the Y flange and the stuff, how can you be sure that all the thicknesses is just going to come out the way the standards say? So there will be some errors, right? Sometimes it's too thin, sometimes it's too thick. When it becomes too thick, especially, you know, when you're dealing with this in the concrete class, the thicker floor doesn't necessarily mean that you're going to have more, because it's going to weigh more as well, right? So they, you know, take everything into the account and always try to come up with the reliability index and convert that along with the death rate and so on. So they have in the end the resistance factor, and likewise the factor of safety. And one more thing that I didn't mention in the beginning is the load combination. Generally, not all the loads can occur at the same time, right? Can you imagine that you are in the building where the maximum earthquake will occur while there's a full occupancy in the building, like everybody is in there, and then maximum earthquake occurs along with the maximum hurricane and stuff like that. So if you want to design something like that, that means you're going to end up with a very, very humongous structure. So it's not practical. All right. So we need to consider the load combination, that which one can occur for real, and design our structure so that it can withstand the proper load combination. And this is the load combination in LRFD. We try not to focus much on this. See, the load factor is greater than 1, and the same for ASD. And this is the example of the load combination. And this states here that for LRFD, for RC only in Thailand. And okay, same concept for ASD, but it's a factor of safety instead. Okay, and all right. So I already mentioned this in the beginning of the class. Excuse me for a minute. Okay, I'll come back shortly. Need to check on my kids. All right. Excuse me, I'm back. Okay. All right. So we already mentioned this in the beginning of the class, the LRFD and ASD concept, and it just states here that if it's a reduction factor, it is always less than 1, and if it's a factor of safety, it should be greater than 1. And generally, what you should know by now is that we have 2 kinds of failure mode in the steel structure. The first one is called yielding, where, of course, your member will yield for lack of a better explanation. The second, it's going to rupture. It's just going to be torn apart into 2 pieces. So you can imagine that yielding is a ductile failure, say that. So it is slightly less damaging. It gives you the opportunity to run away from it because it's going to show some sign, it's going to yield. So the factor of safety is less than the rupture mode, where, you know, everything is torn apart and the failure is called brittle. and it can be more catastrophic. So the factor of safety is 2 for one second. Oh, that's my mother. Okay. Sorry. Anyway, yeah, as I mentioned, the factor of safety for rupture failure is going to be higher because it is more severe. It is a brittle failure. So it's 2, generally 2. And the yielding is 1.67 or 5/3. Okay. Now, you know, I tell you a little bit more about the factor of safety, like from something for the cable car, you know, or the cable for your elevator. Can you guess how big the factor of safety is for the cable of the elevator or the cable car? Then you put people in the cable car traveling between the valley, and then you know this cable, this shuttle has only one cable to support it. Just one cable. If you were in here, how much factor of safety you would like your cable car to have? Huh? Screen is gone. 2.5. Wow, 2.5 is for foundation, you know. I need to reshare it. Okay. Actually, it's 6 for the cable. Meaning in the cable car, you know, when you're traveling to Pukadung, for example, and you want to take the cable car, you know, on the way up, it should be, you should feel okay because the factor of safety is actually 6. Because, you know, you cannot afford this to be torn apart, right? Anyway, so that's it. And it's a small example on how to deal with the ASD, where the you need to use the load combination based on the service load. Service load is, you know, where we don't use any factor to modify the load at all. Generally, we just use the load as it is, and then we compare the load combination with the ASD method, that is the strength, and then we divide the nominal strength by factor of safety. So that's ASD. Okay, service load versus this is moment, so it's nominal moment divided by factor of safety. Whereas in the LRD we use the factored load. They choose to increase the uncertainty in the load by, you know, increasing the load. Where in the ASD, okay, we take the load as it is, but we reduce the strength of the structure. In ASD, they just in LRFD, I'm sorry, they increase the load to account for all kinds of uncertainty, and then they compare this with the nominal moment multiplied by the reduction factor. You can say, I'm going to use the full strength here because I already account for the uncertainty in load by the factor, right? It's a wonderful concept, but you still cannot use the full strength of the structure because you have to account for some uncertainty as well. Okay, so that's that. Okay, generally I wish to, I know that it would be impossible to cover that. I wish to cover the tension members a little bit, but I think it's going to be too much, and we have maybe 15 minutes left. So that means generally we have to find some time, some extra class to deal with this. I hope that you are okay with that. Okay, and anyway, while we have 15 minutes, let's try to begin some portion of the chapter 2, the design of tension member. Can you handle that? Are you still okay? It's not too much on the first day?
Yeah.
Hello? Is it too much?
No, just go ahead, sir.
All right, thank you for your encouragement. Okay, so here's a chapter 2, design of tension members. Okay. So here is something that I already mentioned in the beginning of the class. We are here to design something. We are here to choose the structure that will be strong enough to withstand the load. So whatever we do, the concept is this. You will have the load based on the requirement of the law. And then you will have to come up with something that has resistance greater or equal to the demand from the load by the law. And the resistance that you can try to predict and make sure that it's greater than the load, you can do so, or you can predict by using the AISC specification. I forgot to change that. Now we have 2016. Or if you prefer, you can use the standard by Engineering Institute of Thailand as well. I think we are nearly the finish line. Finally, we have the major update on the EIT. Many of the instructors that are involved in this. Let's hope that we have that available soon. But you must know that it just essentially comes from the AISC here. Okay. So now we have so many kinds of tension members. It's like rods, the bars, the plates, the roll shape or whatever. Yeah. But generally, it's a member that takes tension like that. Okay. So now we need to figure out how many ways that tensile force can destroy our structure. Okay. And to summarize your job, it's just to say that you need to make sure that neither of them will occur. Okay, so we are here to prevent all kinds of failure mode from occurring by choosing, that is, designing the structure that is strong enough that no failure mode will occur. Okay, so here, right now, the AISC specification and the EIT state that for tension members, you have, in terms of strength, it can fail under yielding. That means if you keep pulling something that looks like a rod like this, it can yield, or it can rupture, be completely torn apart into two pieces. So in terms of strength, yes, we can say we have two failure modes for tension members. So now if you have a member carrying tensile force, it can fail in one of these two ways. Okay. And this is what we call strength. But in terms of designing something, you not only have to make sure that your member is strong enough to withstand the load, you must also make sure that it's okay in terms of usage as well. We call that serviceability. It's service plus ability, the ability to service, so to speak. So pronounce serviceability in one word, because steel is a very strong material. Okay, so because it is so strong, we don't need to say use a lot of it. It leads to problem about stability and so on. And still, you don't cast it like concrete. So members come in pieces. You need to find a way to connect them. And sometimes because we need to find a way to connect them, because we don't need to use a lot of it because of the strong nature of it, there's another problem involved. So that's why we need to consider serviceability. Because let's say sometimes the load is so small. Your calculations say that I only need this big section. But sometimes the section is so long. And when it's so long, your structure can wobble because it's long, but it's so slender. So in terms of serviceability, you always need to consider the slenderness of your section and the deflection of your section as well. Okay, so two modes really. The strength, the member is strong enough and it must remain serviceable, not too much deflection, not too slender. Okay, and let's go into, I think we can end this with the formulas. Okay, so first of all, AG is the gross area or the total area of the section. N stands for net, so it's a net area, because sometimes you will lose some part of the area due to the hole punching and so. So you need to reduce that. And when you have the net area, sometimes that net area due to some configuration will not work entirely. So we need to reduce it slightly further, and AE therefore will be used to call that area, which is the effective net area. Okay. So, all right. This is what the specification looks like. If you go into the specification and read it, this is what you're going to face. But yeah, that's a definition of the gross area and the net area. And it says something like this with a lot of alphabets and stuff. So it's a little bit intimidating, right? Anyway, we use this. So when the tension member is going to yield, it's going to yield right here. Right? That's a yield stress. Or when it is going to rupture, it's going to rupture here. So it's going to be the ultimate strength for the rupture. So with that, we can summarize the formula for our design of the tension members into just these two formulas. Considering yielding, the yielding will occur in any gross section. Right? For example, if I draw a picture, let's say this is a steel plate, and I put a hole in it, and I try to apply tensile force here. Okay, when the yielding is going to occur, it's not going to yield where the hole is, because if the area around here is going to fail, it should fail because of the rupture. So the yielding can occur anywhere that the section is full, anywhere. So we can approximate, or we can predict the strength of the member under yielding right away as the yield stress multiplied by the gross area. So there you have it, the first formula for the failure mode tensile yielding in gross section. And please keep in mind that what you now have here is the nominal strength. Oops. Okay. So that means whatever you calculate here, you cannot use it right away. Now you have your calculated strength. you have your maximum strength for tensile yielding in cross section. When you are going to use this as design strength, let's say if you want to design it with ASD, you must use the design strength value, which is equal to nominal strength divided by factor of safety. See, it's really simple. If it's under tension, it's just the yield stress of the material multiplied by the area. That's the first one, very easy, right? And then the second one, again, the calculated strength, the nominal strength, is going to be equal to the ultimate tensile strength, because this is where the rupture occurs, multiplied by the effective net area. We're going to talk about that next time because the time runs out. Okay, and again, the same concept. This is the nominal strength of your section. And if you are going to turn this into the design strength, you must divide this nominal strength by the factor of safety for ASD, and both of them for LRFD, it must be multiplied by reduction factor like this. Notice that here is yielding, so factor of safety is 1.67 or 5/3. This is 2. So okay, that's it. Time is up for today, right? It's to 11:20. Am I right? Not to 11:30. Am I right?
Yes.
Okay, it should be like that because you should be given at least 10 minutes to go to another class and to the restroom and so and so. Okay, so I am sort of a adjunct. Sounds like a adjunct anyway. It's like maybe I'm a temporary instructor. Sounds better. So I don't think it is very nice of me to violate your time more than this. But I have to say that we probably need the extra class to cover all the materials. I hope you don't mind. Okay. And let me stop the record first.